Hi, my name is Nas Nienowski. We're going through this book called Monoidal Category Theory, Unifying whatever, okay? And today we're doing chapter 2, we're doing part of chapter 2, which is categories. Okay, so we're going to come to the main definition of categories. So basic definition, section 2.1, basic definition and examples. Okay, so let's just go through what we're going to do. We're going to remember a few things about what we did last time in the last video, and then we're going to give a formal definition of what a category is, and then we do tens and tens and tens of examples of different categories, and we go through them. Okay, now these examples are going to show up all over. Okay, so for, we're just introducing these new categories, and then we're going to talk about different properties of them. We're going to talk about how they're related to each other. We're going to show more structure that these categories have later on. They're going to be found all over. Okay, so today is the beginning. So let's just go back to sets for a minute. We talked a lot about sets, and what we saw was the main thing was functions. So I want to just say something that I didn't say about functions that I didn't say before. If you have a set S and it is a set T, and you have a function from S to T, okay, so we have to get some notation. Namely, we say the domain of F is S. That's where it gets its values. I'm sorry, that's where it's defined on, and the codomain, okay, of F is T. So this is just a fancy way of saying, these two lines are a fancy way of saying that F goes from S to T. Okay, and let's just remember a few other things that we had about sets. Namely, we can compose morphisms. This composition satisfies associativity. Okay, and also there's the unit laws. What does that mean? You have a little identity morphism over here. You have a little identity morphism over here. And so F composed identity is equal to F, which is equal to identity composed F. Okay, so this is something that set satisfies. Okay, what we're going to see is this idea is going to satisfy by these types of things are going to be satisfied by all categories. So we have to remember what we did in sets, use that as a helpful aid, and then realize what happens. So before we get to the formal definition, let me just say, it's no good. Okay, not the greatest thing. Let me just say, let me give away the story and tell you the following 3 examples of what categories are. Okay, sets and functions. The collection of sets and functions in between them form a category. This collection of directed graphs and graph homomorphisms form a category. You don't need directed. It could be, it's true also for undirected graphs, but fine, we're talking about directed graphs. Next, the other thing is groups and group homomorphisms. Also form a category. Okay, great. Okay, so now that we saw these, let's get in and abstractly not talk about these 3 things, but talk about in general what is a category. Okay, and there's a few different levels to this, and let's get to it. Okay, so a category A, I'm going to call it A. Well, I'm going to call A category A. We're going to also call categories B, etc., etc. Okay, consists of two collections, and we have a lot to say about every one of these. Two collections, okay? The objects of A, okay, and the morphisms of A. The objects are the things, the morphisms are the maps in between the things. So in sets, this was the collection of sets, this was the collection of functions. When we're talking about directed graphs, these were the directed graphs, these were graph homomorphisms. When we talked about groups, these were group homomorphisms. Okay, with two functions, the functions are as follows. The domain, little subscript of A, the domain is a function that goes from the morphisms of A to the objects of A. Okay, and the codomain also goes from the morphisms of A to the objects of A. Okay. And we saw something very, very similar when we were talking about graphs. Namely, we had the source and the target. Okay? And they tell you where every arrow, and here we have maps, just different words, maps, morphisms, where they start from, where they end. Okay, I don't know why that's, okay, this is small letters, okay? Codomain. Okay, so we've seen this before. Let's just write it out carefully. If this is a typical object in a category, this is a typical object in a category, this is a typical morphism in the category, then what we're saying is the domain of F is A, the codomain of F is B. Okay? This is just a fancy way of, this is just functions that show you where the starting point of every morphism is and where the ending point of every morphism is. Okay, great. So let's just reiterate. You have two collections, you have two functions. Hold on. Okay, and now you have two operations. Okay, one is called composition. So that says if you have two maps, morphisms like this, where they're connected, okay, let's just be careful what that means. And again, the formal definition is in the book. The codomain of F is the same as the domain of G. Then you can compose them, and you write the composition the same way we've been writing the whole time, F compose G. Okay, so this was not in directed graphs. Directed graphs didn't have this composition. You couldn't compose maps, but in a category you can compose maps. And furthermore, for every object A, there is a map, okay, identity of A, which goes from A to A. Okay, the way you might want to write this is there's a map in the category, okay, and it goes from objects of A to morphisms of A, okay, and basically identity of A equals ID A. Okay, that special map, there's going to be a special map, and it's going to satisfy a certain requirement. Okay, great. So there's composition and there's identity maps. These are more functions, that the operations that you have to have, and they have to satisfy two requirements. Okay, what's the two requirements that they have to satisfy? Composition is associative, and the unit laws. I just wrote it 2 minutes ago, but let's just say it again. Identity composed F is equal to F, which is equal to F composed identity. Okay, where you have the right subscripts there of which identities they are. Okay, this is true. So for any time you have a map, you compose it with an identity on this side. In other words, you do nothing to it beforehand, you do nothing to it afterwards, then you get back, do nothing to it beforehand or afterwards, you do nothing to it beforehand, you get back the original thing. That's it. That's the definition of a category. Okay, let's just reiterate. You have objects, you have morphisms, you have domains, codomains, composition operation, identity operation, and it has to satisfy these two requirements. Composition is associative, that means dealing with 3 different morphisms, and it satisfies this unit loss. That's it. Okay? Okay, great. Now starts our big list. And here we just go through example after example. The examples in the book are somewhat split up. Computer examples first, and then we do we do computer examples and we do other examples. Okay, but before we do go to the examples, there's a few things that have to be said, just comments about the definition. Okay, 1, I will be calling this a map, a morphism, an arrow. Okay. Okay, so there are a lot of different ways of saying it. Usually I say morphism, but again, in every book it's different. Okay, next, we say objects of A and morphisms of A is a collection. Okay, now what the hell is a collection? Okay, so if you know the lingo of set theory, so we'll say it's a class or it's a set or something like that. But if you don't know that, it's just a bunch of things. Okay, that's what a collection is. It's just a bunch of things. It's a gathering of things. I don't want to get into that discussion about set theory and what can be and what cannot be. We're gonna get into some formal definitions. We're gonna need it. It's important, but not right now. Okay, so right now it's just think of it as a collection. Okay, next, you have an object A, you have an object B. There might be many usually there's many morphisms between A and B. And the way you write it is HOM A comma B. Okay, so this is in the A category, and this is you're looking for those things from A to B. The word hom is from homomorphism. So we use the word homomorphism twice. We talked about graph homomorphisms, we talked about group homomorphisms. So we're getting the same type of word there. So this is the set of homomorphisms or morphisms. By the way, maybe we should write it like that. Homomorphisms is another thing, but we don't really use that. But maybe we should. Okay. So you could talk about the collection of homomorphisms whose domain is A and codomain is B. Okay? Now, let me just show you from this point of view what composition is. Composition is, we describe it with a little circle, that's a map, and it goes as follows. It's from HOM of A, B comma C, cross HOM of A comma B. Okay, so give me a map from A to B, and give me a map from B to C. Then there's going to be a map from A to C. Okay, and we can write this like this. Here's F, here's G, oops, here's F, here's G, here's a pair of them. Okay, and this goes to F composed G. F goes from A to B, G goes from B to C, F composed G goes from A to C. Okay, and that's a little map. And again, this little map has to satisfy a more complicated thing called associativity. Okay, great. So this is just I'll spend a lot of time with this. This is just some comments on the definition of a category. Okay, but before we let's start with the big example, with the examples. Okay, and let's use a different pen because this pen is almost dead. Okay, so here's the trivial example. You ready? We call this example 0. Okay, this is our first category. And you ready? It's basically the empty set. It has no objects. It has no morphisms. It's just the empty category. Okay, so this is called sometimes the empty category. Okay, as opposed to that, here's another category. It has one object, and it has one identity morphism. Okay, and this category we sometimes call 1. Okay, so these are finite categories. This is trivial, this is 1. Okay, here's another category. Okay, it's, by the way, the fact that I call this 1 is a star, I could have called it A. Just like a one-object set, there are many one-object sets, so too there are many one-object categories. Okay, so this is a one-object category with one morphism. Okay, here's another one. Okay, this is identity on A, this is identity on B. What that just means is names of objects are not really important. So to A and B, I could have called them X and Y, I could have called them C and D, I could have called them anything, Jack and Jill. Okay, okay, so here's another category, we call this 2. Okay. Okay. Here's another category, and again, different authors have different notations. Here's A, here's B. You must have an identity on every single object, so that I can't get rid of. That's identity on B. Okay, but this doesn't have a morphism in between them. I call that 2 with a little circle on the bottom of that. Okay, it has a past. That notation has a past, but it doesn't pay to get into it. Okay, next, here's another category. It has an object A, it has an object B, it has a morphism like this and like this. It has an identity here, it has an identity here. Okay, as time goes on, I'm gonna not put the subscript of the identity because you already know it. If it's coming from A, this is identity on A. If this is coming from B, it's an identity of B. Okay, great. This has 2 morphisms, okay? But these 2 morphisms are inverse of each other, which means, we'll get into that later on, that means if you go this way and you go this way, you get the identity. If you go this way and you go this way, you get the identity. So that's it. This category has 4 morphisms. By the way, this category has 3 morphisms. This has 2. This has 4 morphisms. But the main thing is, if you go one and then the other, it's just the same thing as going. So you start off at B, go this way, then go this way, they compose. That's the same thing as just the identity here. Okay, and this is called 2 with an I on the bottom for isomorphism. Okay, one more category. So how about this? A, B, C. Don't forget your identities. Okay, and this is like that. So let's count how many morphisms. This has 1, 2, 3, 1, 2, 3. So this has 6 morphisms. We call this category 3. Okay. And obviously, you can go on with this and come up with more. These are all finite categories. They have a finite number of objects. They have a finite number of morphisms. Most of the categories we deal with will definitely not be finite, but they will show up. Okay, finite categories do show up. Okay. Another point, given any set S equals A, B, K, I don't know. Okay, it's a nice set. I can form a category. The objects are A, B, K, And the morphisms are trivial morphisms. Identity on A, identity on B, identity on K. Okay? Okay, so for every set, you can have 10,000 elements. You have what's called, you ready? The discrete category of elements. Okay? What this says really is that instead of thinking about sets anymore, you can now just think of discrete categories. Okay, so that's going to save you a lot of room. Okay, it has to have the identities because that's part of the definition of a category. So it has to have these identity morphisms, but there's nothing in between them. Hence the word discrete, they're separated. Okay, next. Okay, so let's go through some more examples of categories, but we're getting into the real examples. So let's talk about that. So let's start with some examples from computers. It goes as follows. What does a computer do? Well, what does a programmer do? He writes functions. What's a function? Well, it's something that takes a certain amount of data, of different types of data, and outputs certain types of data. That's what functions do. They have inputs, they have outputs. Okay, the inputs and the outputs are described with things called types. Okay, I'm not going to be formal about this, but basically a typical function would take an integer cross a character cross a string, okay, cross a real number. So a typical input might be a whole integer, a character, a string, and a real number, okay? And you might get an output. The output is an integer cross a double. That's another thing that computer scientists talk about, cross a real, cross a string. Okay, so this is a typical type of function that computer scientists or computer programmers might deal with. Okay, so now I want to talk about, you ready? So, I'm so sorry. This is a type, 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 this is a type. These are types of data that you could have. And when you take a cross of it, so this whole thing is a type. In other words, you have this way of combining types to get other types. So this is one type, this is another type. Okay, now we could talk about a category. So the category is called computable functions. Okay, and so we usually have our categories are usually bold-faced. So the category of computable functions, the objects are types. Okay, and you have to see what types your computer can deal with. Sometimes some programming languages do have doubles, some don't. Okay, et cetera, et cetera. And the morphisms are computable functions. Okay, what do I mean by that? They're functions that accept inputs of this type, have outputs of this type, but you can write a computer program that does this function. Okay, so they're called computable functions. Okay, now let's go through some quick things. First of all, you can compose computable functions. You just take one program and follow it by another program. That's a composition of computable functions. Okay, the composition is associative. Okay, another thing is, for every single list of types, there's an identity on the list of types. Okay, and this identity function is computable. It's the stupidest function possible. Namely, it accepts some data and it outputs some data. Nothing intelligent. Okay, and it satisfies, so we have the objects, we have the morphisms, we have composition, we have the identities, okay, and it satisfies associativity. In other words, you do 3 of them, you get them the right way, and it satisfies the identity. If you use the stupid program that doesn't change any of the input or the output, then you get back the original function. Okay, so this is a major category that computer scientists deal with all the time, and they want to find out different properties of this category, etc. Okay, I told you about this book that I wrote called Theoretical Computer Science for Working Category Theorists. That book spends a lot of time with this categories and looks at subcategories of it, looks at quotient categories of it, looks at lots of fun things about that. Okay, next, let's talk about logic. Okay, just want to point out, this book is called The Unifying Concepts. The idea is as follows. We're going to have examples from all over, okay? Computers, logics, math, algebra, physics, different things. Okay, so you should expect to see examples all over. Okay, so let's talk about another category. It's called prop for proposition. Okay, and this is what logic is all about. It's about propositions, statements that are either true or false. Okay, so the objects are going to be propositions. Again, statements that are true or false, and the morphisms are very interesting. Given 2 propositions, you know, today is Tuesday, tomorrow is Wednesday, or something like that. George Washington is the king of France, and 2 + 2 is equal to 4. There's a morphism in between them if P implies Q. If one thing implies Q. If one proposition implies the other proposition. Okay, the logicians sometimes use the word entails. Okay, so this is a central idea in logic, this proposition. Okay, great. So this is a category. The shocking thing about this category is that the first time we see a category where there's only one morphism, there's at most one morphism between 2 objects. So again, given 2 propositions, you have 2 possibilities. There's no morphism in between them, or there is one. Now again, every single morphism has an identity. P implies P, Q implies Q, P implies P, Q implies Q. But question, is there a morphism in between them? Yes or no? Well, sometimes there is, and sometimes there isn't. And that's the interesting thing about propositions. Okay, we're going to see later on that this category is going to have different operations on it. In other words, we're going to be able to take two propositions, and we're going to take the and of it, the or of it. We have something called the internal ham of it. We're going to do lots of different things. Okay? At the end of chapter 4, we're going to have a whole mini course based on this category. We're going to deal with other aspects of this category too later on. Okay? Okay, so those were 2 nice computer science-y, math and computer science-y things. Okay, now I want to talk a little bit about algebra. Now, a lot of books for category theory are written for computer scientists, are written for mathematicians who know a lot of mathematics before and might have had abstract algebra. Okay, this book is not for them. They're welcome to listen in. Okay, but I do not assume that you know a lot of abstract algebra. And I'm not going to spend a lot of time in abstract algebra, but a lot of examples come from there, and so we're going to talk about them. Okay, and so we're going to talk about 1, 2, 3, 4, 5, 6, 7, 8 different types of algebraic structures, and I'll explain to you what I mean by an algebraic structure. Okay, and we're going to put these structures into order in a type of Venn diagram. So the Venn diagram is on page 592 of the book. I'm going to show you the Venn diagram, but then we're going to build a Venn diagram from scratch. Okay, there's some nice Venn diagrams here at the end of the book. We're going to build this Venn diagram as we go along. Okay, so let's build it over here. Okay, so let's talk about the first type of structure. It's a little obscure, but we want to see the whole picture, and that's what category theory is all about, seeing the whole picture, so we have to include this. So a magma, okay, a magma is a type of structure. Okay, and what do I mean by a structure? Well, it's a set, we'll call M for magma, okay, and an operation, a binary operation. So we saw what that was in last video, okay? That's a magma, okay? Nothing else. We don't make any requirements on the magma. We don't describe, we don't have a unit, we don't have anything else on this. It's magma. Magma is the, like, I guess the stuff that comes out of a volcano or something. It has no structure to it. It has no point, so hence the word magma. Okay, so let's draw our Venn diagram here. We're going to need a lot of room, okay? And these are magmas. Okay, great. Now, magmas are not very interesting. I have a few examples in the book of different types of magmas, but they're not very interesting. Let's look at another structure called a semigroup. Okay, okay. What's a semigroup? Maybe this shouldn't be here. What's a semigroup? A semigroup is a magma but it satisfies one requirement. Namely, this single operation is associative. Okay? So it's a requirement, namely, that x times y times z, it doesn't matter how you do it, they're equal. Okay, so that's called a semigroup. The word semigroup probably comes from what we had, what was the definition of a group, which is probably the earliest algebraic structure. So this is to be thought of that. But really, this is a magma, a special type of magma called semigroups. So we're going to write them like this. Semigroups. Okay. Okay, so you have magmas and you have special type of semigroups like that. Great. Let's talk about another structure called a monoid. Okay, and let me just say, this book is called Monoidal Category Theory. It's based on the word monoid, and so we're going to see this over and over, and we're going to spend a lot of time today going through the definition, what is a monoid. But let me give you quickly what the definition is, okay? It's a magma okay, that's associative. Okay, so it's a semigroup. A monoid is a semigroup, but it has, not it satisfies another requirement, but it has extra structure in it. What's the extra structure? Not only does it have a set, but there's a distinguished element in that set called E. There's another element in that set called E. Now I could write that other element. We know how to do that. We could write it as follows. Something that picks out what the E is, but I don't want to do that. We can do that, but let's not do it. But it satisfies another requirement, namely, take any element X, multiply it by E, you get X. Okay, multiply it either side. Okay, so it has a unit or an identity, depends on what you want to call it. So that's a monoid. Now, we have to do something a little bit interesting. This is, I want to talk about the set of monoids. Now, I don't want to say that monoids are special types of semigroups. In other words, they're not semigroups that satisfy another equation, okay? A semigroup is a special type of magma. It's a magma that satisfies a special another equation. But a monoid, it satisfies an extra equation, but it also has more structure. It has this extra E. We require it to have this extra E. So it's not just a special type of thing, it has something else to it also. Okay? So, you know, you could talk about machines and you could talk about souped up machines, but then you can have other machines, not that are faster or better, but they have other operations, they have other things that it can do. And so we want to talk about that. Okay, so I don't want to draw just a regular line to make it think that just like this is a special type of this, this is a special type of this. So what it is it's related to this. Monoids are related to semigroups. Monoids have extra structure. And so I'm going to do it like I do it in the book. Okay, and I'm going to say it like this. Now, later on, we're going to understand this distinction between a special type, something that satisfies more equations, versus new operations, but not right now. Okay, great. Let's talk about, okay, let's talk about this. Now we're going to talk about a commutative monoid. Okay, a commutative monoid. So what's a commutative monoid? It's a monoid, which is a semigroup, which is a magma, but it has an extra element, E, okay? And it satisfies another equation, namely, for all x and y, if you multiply them, it doesn't matter, x times y is equal to y times x. Okay? Now, we're going to see many examples of commutative monoids. We're going to see many examples which satisfy this equation. We're going to see many examples which don't satisfy this equation, but we have this. Main point is, this is a special type. The commutative monoid is a special type of monoid. So, okay. Now, I'm going to draw this, but I'm going to draw this like this, not the whole thing. I need space over here. So this is a commutative monoid. Okay. So we so far have 1, 2, 3, 4 different structures. And again, this is a special type of this. It's a regular monoid, but it satisfies, it has an E in it. So if you want, you can write an M, and it has an E in it. But here and it has the operation, but here we require that this operation satisfies this commutativity. Okay, so let's just think about addition that you learned in 3rd grade. A plus B is equal to B plus A, okay, but A minus B is not equal to B minus A. A times B is equal to B times A, but A divided by B is not equal to it. Okay, so sometimes things do have to satisfy this operation, sometimes these things don't. Okay, in the book I have a giant full page examples of all these different structures and the number systems that satisfy these equations and don't. You really have to stare at it for a long time and see why this is in here and not in there, etc., etc. I'm not going to go through that in this lecture, but it's a really nice page that shows you natural numbers versus real numbers versus rational numbers, what satisfies what properties. Okay, next. Next is something called a group. Oh, but we saw a group before. Okay, so let me tell you what a group is. A group is a monoid, not necessarily a commutative monoid, a monoid. So M, comma E, it has that. But it also has another operation, which is, we saw this already, called the inverse. Okay, there's another operation called the inverse. Okay, so what that is, given an element x, there's another element x minus 1, and if you multiply that by x, you get the identity. Okay, we saw this at the end of section 1.4, what's a group, but now we're seeing it from this point of view. It's an operation, it's an associative operation, it's an associative operation with an identity and with an inverse. So, I'm sorry, I left out the, so it's a set with an operation, with an identity, with an inverse. Okay, now, because this is not a special type of monoid, but it has this extra structure, okay, so I'm not going to make a regular line, I'm going to do the squiggly again. So again, what's a group? It's a monoid with this extra operation, and so we're going to draw it like this. Okay, and this is a group. Okay, now, some groups are commutative. The multiplication is commutative, like that. So this is commutative monoids. The things in here, the operation is commutative. The things over here, the operation is not commutative. Okay. Okay, so what I want to do here is I want to say these are commutative groups. Okay, they also have another name called, another name called abelian groups. Okay, that's right there. Okay, that's this in-between thing. Okay, great. We have two more structures. Okay, one is called a ring. Okay, let me tell you what a ring is. A ring is a group, I'm sorry, even more. It's an abelian group, it's a commutative group. Okay, so what's a ring? It's an abelian group. Okay, so let's just say what that is. That means it has a set, it has an operation, it has an identity, it has an inverse, it's commutative, okay, but it has another operation. Okay, now let me explain to you why I'm doing this. Think about the natural numbers. You can add natural numbers, okay, and if you want the inverse of that is subtract natural numbers, but there's another thing you can do with natural numbers, namely, you can multiply them. So you have these two different operations, plus and multiplication, and they come together. So this is a group. It has another operation. I think in the book I do it like this. That other operation I just make as a circle with a dot inside. Okay, but it also has another unit. Okay, just think of the natural numbers. You have addition and subtraction, and the unit for that is 0. X plus 0 is equal to x. Okay, but now a ring deals with two operations, not just star, but 0 with a dot in it. Okay, and this also has a unit, and we're going to call that u. So if you think about the natural numbers, this is multiplication, and the unit for multiplication is when you multiply something, do you get the same thing over? And the answer is x times 1 is equal to x. Okay, so if you think about it, think about the natural numbers. You have 0, which is the unit for addition. X plus 0 is equal to x. And you have 1, which is the unit for multiplication. X times 1 is equal to x. Okay, so that's an abelian group. There's a further requirement, namely, okay, so it has this extra operations, but there's a further requirement, namely, distributivity. So let me just say what that means. X plus, X circle dot of y plus z, or star z, is equal to x circle dot y star, parentheses, x circle dot z. Okay, so that's a distributive property. So whenever you have two operations, you want to know how much they respect each other. Okay, and so we have that. Okay, there's another one also, and you'll find it in the book. Okay, so let's just go through this. What's a ring? It's a group which is commutative, so it belongs in here. It's a commutative group, but it has two extra operations. It has another binary operation. Think of you multiplying two things, and it has another unit. So we're going to put it right over here. Shoot. 1 second, we made the wrong type of line. Why? Because this is an extra structure. This is extra structure. It's not a special case. It's not just satisfying another equation. It's an extra structure. So we need wiggle like that, and this is called a ring. Okay? Okay. And finally, the last one is called a field. Okay? Let me tell you what a field is. A field is a ring. Okay? But this multiplication also has an inverse. Let's go through this. What's a group? A group is a monoid where the multiplication has an opposite operation that undoes it. Okay, and then we made a ring, and we said, here's another operation, circle with a dot in it. Well, if you put an opposite operation in there, and I'm leaving out a few details about this, okay, then you're going to have another thing. I don't remember how I described that opposite operation. I probably didn't. I probably described this with a minus and this with an inverse. Okay, anyways, where does a field go? Again, a field is a special type of ring which has this opposite operation which undoes what the multiplication does, and it goes here, field. Okay, so here you have 1, 2, 3, 4, 5, 6, 7 operations, 7 different types of structures. Okay, and we're going to get into it. We're going to get into some of them. Let me just tell you three things that are going to play a major role in this. Monoids are going to play a major role in everything we do. Groups a little bit later on, and we're always going to be working with the real numbers or the complex numbers, and these are two fields. These are two fields where you can add things, subtract things, multiply things, and divide things. The inverse operation is usually related to something called division. Okay, so here's 7 different algebraic structures that we're going to deal with. What's an algebraic structures? They're sets with different operations. Okay, some of the operations are binary operations, some of the operations are unary operations, etc. You don't have to waste your time while I erase the board. Okay, so we have all these different algebraic structures. I want to meditate, I want to concentrate on one of them because this book is called Monoidal Category Theory, and it's about something related to monoids, and so we're going to see this over and over again. So I want to just dive into one of those algebraic structures. We dived in last video into the algebraic structure of groups. I want to dive into the algebraic structure of monoids. And again, because we're going to see diagrams that are variations of this throughout the text. Okay, so let's just say what a monoid is. A monoid is a set, okay, with a binary operation. Okay, and a particular element, E, member of M, which we can write as a map from there, we'll call that map V, till M. Okay? Okay? So that's it. It's a set with a binary operation and a constant operation or a zero array operation, or just an element, a particular element, and it has to satisfy 2 requirements. And I want to write the requirements, but instead of writing them as equations, they have to satisfy certain axioms. I want to write them as maps as diagrams. So we saw this with groups, but let's do it again with monoids. It's the same diagram. Okay, this is the operation, this is the operation, and here we're going to have, I don't know, the operation cross the identity, and here we're going to have the identity cross the operation. Okay, basically this says these two get together and then they become two things and then they multiply, or these two come together and they become one thing here and you multiply it along here. This is associativity. We saw that before. And now let's do the unit. Let's be a little bit more careful with the unit. It goes as follows. Okay, so this is a set with one element. This is a set, okay? This is what the monoid is, okay? And I want to talk about M cross M, and I want this to pick out the E in here. So this is going to be V cross identity on M. Okay, don't touch what's in here, just pick out that E. Okay, great. I want to also do it on the other side also, so I'm going to have M cross the single element, okay, and this is identity on M, just like we had before, cross V. This picks out the thing, picks out this, picks out the E in the monoid, okay, and what I want is as follows. Let's multiply these things, okay, and what we get is as follows. This is an isomorphism. This is a very nice map. We know what an isomorphism of sets are. This diagram is happening in sets. This is all about sets. Basically, M cross one element is basically the same as M. Okay, so let's see what this is going to do. This is going to go like this. A typical element here will be x comma little m, okay, and here it's going to go to e comma little m, okay, and now we're going to multiply those, and so we're going to get e times little m, and what this says is going this way, well, that should just be equal to e, m, okay. That matches up with that. Okay, and of course you could do it on the other side. This is the definition of a monoid. Again, what is it? It's a set, a binary multiplication, and a singleton, and it satisfies associativity and this unit rule. Okay, but I wanted to show it like this. Okay, we're going to see many, 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 many variations of these two diagrams over and over throughout the book. Okay, so great. I want to talk about some examples of monoids. The book has a lot of different examples of monoids, but I want to talk about two examples that are very important for the rest of category theory. Okay, one example is as follows: take any category, A. Take any element in the category called little a. Okay, now there might be maps going here, and there might be maps going there, and there might be maps going here, and maps going here, and maps going here, and maps going all over, etc., etc. Okay, but I want to talk about an interesting thing. Take this object A. I could take any object, okay, and I look at Ham within A, so this is a homomorphisms from A till A. Okay, turns out that that's a monoid. That's the set of all morphisms from A to A, so you might have to go like this, and this, and this, and go around here a few times, go here, that comes back. And then you can go here, and then here, just here, and then here, that goes back. here is a monoid, going here, going around 5 times, going here. Lots of different maps from A to A. It turns out these are this set, this collection of homomorphisms forms a monoid. Let's think about it. So this is the set, okay? And now what's the operation? Well, if I take some map from here around to here, and then I follow it again around to here, I'm going to get another map from here to here. So just composition of maps. So again, if you have some wild crazy map from A to A, and then you have another wild crazy map from A to A, then you have a wild crazy map from A to A. Okay, that's one thing. Great. That shows that that's a monoid. What is the unit? The unit is the identity on A. Okay, so that's an example of a monoid. It's going to turn out that every single monoid can be written, it can be thought like that. Sorry. Okay, that's an example of a monoid. We'll talk about something else in a second. Okay, let me make sure I'm centered. I'm centered. Okay, great. This is no good. Okay, we're going to hold on one second. Okay, so that's what a monoid is, which is a particular example of an algebraic structure. But now I want to talk about homomorphisms of algebraic structures. Okay, and the idea is you have one algebraic structure, you have another algebraic structure. What are the type of maps that you have in between them? And basically they're as follows. Take, say, a monoid or a semigroup or a magma or anything you want. Okay, take another one of the same type of thing. Well, what is a homomorphism? Well, it's a map from the underlying set of this, the set of this, to the set of this, but we make requirements, and the requirements are all the same requirement over and over and over. Namely, this function has to preserve the operations. Okay, what do I mean by preserving the operations? Well, I'm going to give you an example. I'm going to give you examples. So for, let me write it out as equations. So if you have an operation in this, and you have x and y, so you can do that. So this is an operation in M, okay? But what you want is that should also be equal to that's an operation in M prime. Okay? So basically what this says is you can do the map, but I want you to preserve and realize that this comes from two elements in M, okay? And it should be the same thing as taking the image of F in M prime, taking the image of Y in Y prime, and then doing the operation there. That's what it's called, preserving the operations. So this is for a binary operation. Let's say we had a trinary operation, so then it would be something like this. We'd have some type of operation, we'll call it O, of x comma y comma z. It has three inputs into it. It's a trinary operation. Well, I want this to equal to, so take these three things and do some operation with them. That's the O. Well, I want this to be equal to O prime, okay, this trinary operation in here of f of x comma f of y comma f of z. Okay, this is what a homomorphism is. It shows that the operation commutes with the function. So it's a function of sets, but we want to make sure this is true. Okay, let me show it to you. This is a trinary operation. This is a binary operation. Let's say what a unary operation is. So let's say you have f of x, and let's say this has a -1 on top, so that's a unary operation. Okay, well, guess what? We want this to be f of x with a -1 prime. Okay, so that's a unary operation in n, that's a unary operation in M prime. Okay, and finally, let's talk about a not 3, not 2, not 1, but 0. Okay, and what that is a zero area operation just picks out one element. Well, I want you to pick out the same element. Okay, main point is, okay, so this is going to happen. So we have lots of different things. A magma only has a binary operation. Well, guess what? A magma homomorphism will have to preserve that binary operation. A semigroup only has a binary operation. Don't worry about that. A monoid has a binary operation and a zero area operation. Okay, a ring has, I don't know, 4 or 5, whatever amount of operations, these functions have to preserve those operations. Okay, great. Now, I'd like to write this and this as commutative diagrams, and I think I did it already in the case of groups, but let's do it again. Not good, not good, not good. So let's do it this. Okay, for the next video, we're going to have to get a better eraser. That's fine. Okay, so for binary, for a monoid, what does it mean for a graph to be a homomorphism? And again, I'm drawing this picture only because it's going to show up over and over again, or variations of it. Okay, well, what is it, a monoid homomorphism? It's a map from here to here, such that this is F, a map from here to here, this is F cross F. Okay, let's see what this means. Okay, so let's do this. X comma Y over here. This is going to take it to F, so this is an ordered pair within this. This is going to take it to an ordered pair in here, namely F comma X, F of X comma F of Y. Okay, we're going to apply this function to here and here. Okay, we're going to multiply them here. Okay, and we're going to get F of X times, but with the comma there, with the prime, of F of Y. Okay, and this is going to go here, and this is going to be X times Y, and we're going to apply F to it, F of X times Y. We insist that those two are equal. Okay, so that's exactly what I drew before, but here we have a nice diagram. We're going to see this diagram over and over in many different places. Let's just do one more. Okay. Again, this is a monoid homomorphism. A monoid has a zero area operation. What's a zero area operation? So we have that, chooses an element, we might call that V, chooses an element of M. We have V prime, chooses an element of M prime, and we want the function to preserve that unary operation, and we can see this very, very clearly as follows. Ready? The star here goes to E, which goes to F of E, and the star here goes to E prime. And we want this to commute, so we get this. Okay? Okay. As time goes on, I'm going to write less and less equations and write more and more pictures. I like pictures. You like pictures. Category theory is about pretty pictures. I say that sometimes just to upset people, but there's a certain truth to it. Great. Let's go. Okay, great. Now, what can we say about algebra homomorphisms? Okay, what can we say about them? Well, we have two things to say about them. Namely, if you have some type of algebra, I don't care, a ring, a field, okay, and you have another field, and you have a field homomorphism, and then you have a field, and a third field, and a field homomorphism. We'll call this G1, we'll call this G2. Guess what? You can compose them, and the book goes through it very carefully, but when you compose them, the preserving of the operations are also preserved. Okay, and so you get G1 composed G2. Well, guess what? This composition is, you guessed it, associative, and the unit law is satisfied. Okay, I already did the associative a million times. Unit law just means G1 composed identity is equal to G1, which is equal to G1 composed identity. Okay, and you have it for any graph homomorphism. I'm sorry, for any algebraic structure homomorphism. So you always have this associative, you always have this unit law. Very nice. What does that tell us? Well, that tells us that all these algebraic structures form categories. So this whole chapter is all about finding examples of categories, and here we have a whole list of examples of categories. So let's go through it very carefully. Okay. So there's going to be a category called magma. Okay, the objects are magmas, the morphisms are magma homomorphisms. Okay, there's going to be a category called semi-group. The objects are going to be semi-groups, and the morphisms are going to be semi-group homomorphisms. There's going to be a category of monoid. Okay, it's boldface. Okay, the objects are going to be monoids. The morphisms are going to be monoid homomorphisms. We're going to have commutative monoids. Okay, we're going to have groups, G-R-O-U-P. We're going to have abelian groups. We're going to have rings. We're going to have fields. Okay? Every one of these is a category by itself. Every one of them, the objects are the structure it's called, and the morphisms are homomorphisms of that structure. Okay? And these are going to be, we're going to build a lot with this. And I told you before, we're going to deal a lot with this and a lot with this, and we're going to deal with a few of these. Okay, so we're going to show up. Okay, and later on, chapter 4, we're going to see how these different algebraic structures are related to each other. And it's quite interesting. And then in chapter 8, I just want to foreshadow a little bit. In chapter 8, we're going to talk about algebraic structures in general. There's a million other types of structures we could talk about, and we're going to just learn how to define them and use these diagrams in a really, really important way. So chapter 8 is all about describing structures. How do you make structures? That's what it's all about. These are special types. These are algebraic structures. Okay, so that's algebraic structures. And algebraic structures, like I said, there's millions of them. But mathematicians are also interested in something else called topological spaces. We're going to see the definition, the formal definition, but it takes years to get an intuition of what it's all about and why you need the formal definition. So what are topological spaces? Basically, they're blobs of spaces, but they also have subsets which describe nearness. When is one space, when is one point in the space, one dot, one element in the space next to another one? So you have that. Okay, let's be a little bit formal about it. Okay, and the formal is a topological space is T, a set of points, and tau, a subset of subsets of points. So each one of these is a subset of the points. So a tau, T, which is called the topology on the space, okay, it is it tells you what's closer, what's far, and things like that. And so that's very, very nice. But we have some requirements on tau, namely, okay, we have 4 requirements, namely, tau contains the empty set. So the empty set is a subset of all the elements. Tau contains the entire set, okay? And it's closed under finite intersection. Let me just say what that means. If you have S1, which is a subset, S2 is a subset, S3 is a subset, S4 is a subset, all of these are subsets, then the intersection is also a subset. Okay? One more requirement, closed under any, or it usually says arbitrary union. Okay? In other words, take a bunch, could be infinite number of subsets. If you take the union of them, all of them, that's also a subset. Okay? So any tau that satisfies these, 1, 2, 3, 4 requirements is a topological space. Okay? Okay, great. Okay. We have 2 topologies that we're very much interested in, okay? Namely, let's say you have a topological space and you have a topology. So there's 2 types of interesting topologies that you can talk about. One is tau equals the whole power set of that. In other words, just let it contain everything, every single possible subset, okay? And this is called the discrete topology. Okay? In some sense, this is the maximum amount you're allowed, okay? Every single thing is related to every single else. It's not that interesting, okay? It doesn't make it that interesting. And the other one is tau is equal to the empty set and the entire set, and nothing else. Turns out that this is closed under finite intersection, it's closed under all intersection, it's closed under union, so that itself is a topology, and this is called the indiscrete topology. Okay? So that takes care of that. Okay? So basically, any topology is somewhere in between here. So it doesn't contain, typical topologies, they don't contain every single subset, but they don't contain just the bare minimum either. They contain more than that. So somewhere in between these 2 things. These two topologies are the extremes of topologies. Okay, great. Now, we're not interested only in topological spaces, we're interested in functions, morphisms between topological spaces. And so the idea is as follows. Given f, which goes from t comma tau, okay, let's change that. Because let's change it to x comma tau, okay, and y comma sigma. So let's say what that is. This is a set of points and a set of subsets of points, okay? Well, we have a map like that. So what is the map like that? Well, just like in algebraic structure, it's a function f, it's a function from the set of points here to the set of points here, okay? But it satisfies a certain requirement. We wanted to somehow respect these open sets, and it's a little bit strange to see the first time, but basically it goes as follows. If this is x, and this is y, okay, and this is some subset, so we're going to call this, we'll call this s, little s, and s is a subset of y, okay, then what we require of this f is as follows. F minus 1 of s, of s, okay? In other words, those things that go to this open set if you look at that, that's also an open set. So what we say is, if S is in Y, that implies that F minus 1 of S is not only is it an X, but it's an element. I'm sorry, I don't want S is in Y. I want S is an element of sigma. That's that. That's an element of tau. So what this says is that the pullback, the pre-image of any open set here is an open set there. Okay, and again, what this such a map is called a continuous map, and it's hard to. I mean, these are the things that you learn in math classes. We're not going to spend a lot of time dealing with the details of it. The main point is, ready, is such continuous maps can be composed. Okay, so if you have F from one to the other, and you have G from another topological space to a third, so then the composition works out. And this composition is associative. And you guessed it, there's a unit. So basically every topological space has a silly continuous map called identity on T. Okay, and the unit laws are satisfied. What happens when we have this? We're going to have a new category, and it's going to be called top. Okay, let's just go through it. The objects are topological spaces. The morphisms are continuous maps. So that's pretty straightforward. Okay, great. One more, before we, okay, sorry. So that's the end of our examples from math. We have lots of algebraic structures, we have topological structures, and that's fine. Now we're going to go on to more physics type examples. Sorry about this stupid board. We're going to figure out how to do this properly soon. But it's not only the board, it's the marker. Okay, great. So let's talk about physics, examples from physics. So one of them is called the manifold. Okay, what's a manifold? Well, and again, I'm just giving the intuition. It's a topological space, but it has the following property. Let's say this is a two-dimensional topological space. Then at every point at every point of this topological space, it looks like two-dimensional R2. Okay, so there's like a little neighborhood of it that looks like the reals cross the reals. That's what a two-dimensional manifold looks like, is. Okay? And every point, it has the feel of R cross R. Okay, now you might say, hey, R cross R goes forever and ever. Well, this is going to be somewhat open. It doesn't matter what that, but it looks like. It looks like that. Let's talk about what a one-dimensional manifold looks like. Okay, at every point, there's a circle around it which kind of looks like the real numbers. Okay, and in three-dimensional space, every point in it is going to look like three-dimensional R to the third. Okay, so an n-dimensional manifold, every single point has a feel of looking like the Rn, or real numbers to the nth power, okay? And the point is as follows. You spend a lot of time, if you ever took calculus, you spend a lot of time being able to take derivatives and integrals and stuff like that, but you learned how to do it over the real numbers. Okay, great. Now we want to apply that to the real world, okay? And so the real world is made out of things that you might call manifolds. And the point is, they're kind of topological spaces. You have the notion of nearness and farness, okay? But you also, at every point, you can somehow say, you know what, this is close enough to the real numbers so that I can so that I can integrate and do differentials and do what calculus does. So that's what a manifold is, and that's why it's important to physicists. That's why they like it, okay? Because you can do things like that. Let me just give you some examples of one-dimensional manifolds. This is an example of a one-dimensional manifold in the sense that this is what's called open. It doesn't stop at a particular point, okay? And here's another example of a one-dimensional manifold. This line, this circle, is a one-dimensional manifold. At every point, it looks like the real numbers. And there's no point where it's even gets close to something like that. So these two are examples of one-dimensional manifolds. As opposed to that, here's two examples of things that are not one-dimensional manifolds. Okay? You see here, it stops at a point. It's not open, okay? As opposed to going on, having a thing of going on forever. And here's another thing that's not a one-dimensional manifold, okay? And why not? And the answer is, here it looks like R1, here it looks like R1, here it looks like R1, here it looks like R1. But there's one point here where it doesn't, right over there. When you have three things coming together, that's not R1. Let's make sure that I'm in the camera. Yeah, I'm in the camera. Okay, so certain topological spaces are manifolds, certain topological spaces are not. Okay, between two manifolds, so if X is a manifold and Y is a manifold, you could talk about maps between them. Okay, and so think of manifolds as special types of topological spaces. They're topological spaces but with more structure. But the main point is a continuous map between two manifolds can also be a map of manifolds. Okay? And that's a stricter requirement. Basically, we want that not only should it be continuous in terms of the open sets in this one and the open sets in this one, but it should also somehow respect those real coordinates, those things that it's close to the real numbers. Okay? And such maps are usually called smooth maps. Again, it doesn't pay to get into details of what it's about. Main point is smooth maps compose, they're associative, they're identities, so we have the category of manifolds. Okay? But we could talk about special types of manifolds. We could talk about n-manifolds, which are n-dimensional manifolds. Okay, and so you have the category of one-dimensional manifolds, the category of two-dimensional manifolds, the category of three-dimensional manifolds, the category of four-dimensional manifolds, the category of n-dimensional manifolds, and you have all of them together, the category of all manifolds whatsoever. So lots of different examples of manifolds. Okay, great. So that is perfectly legitimate. Let's do another example. Let's talk about another example that physicists like to talk about. Okay, and we're not really going to spend a lot of time on this here, but we will spend time on it later on at the end of chapter 2, and these are called K is some field, usually thought of as either real numbers or the complex numbers. Okay, and so we could talk about K vector spaces. Okay. This will be fundamental later on. K vector spaces, these are something called vector spaces that are based on either the real numbers or the complex numbers. Okay, what are they? They're algebraic structures. Okay, they're algebraic structures, and they're all about linear algebra, and we're gonna have an entire mini course based on them, so I don't have to talk about them right now. However, between two K vector spaces, so you can have a vector space here and another vector space here, okay, there's maps between them. Okay, and the maps are called linear transformations. Okay, and this is fundamental for linear algebra, so they're called linear transformations. And guess what? The maps compose, they have associativity, they satisfy a unit, and so what we have for every single K and we're usually going to deal only with that, you have the category of K vector spaces. Okay, it's written like that, K vector spaces. So given a real, this category, the objects are K vector spaces, and the morphisms are linear transformations between them. This will be central in all of, for C, it'll be central in anything quantum, etc., etc. Okay, let's see what other things that physicists and mathematicians are very, very, very much interested in. We will talk about these here. But I assume this, you see, many people haven't seen topological spaces, but the next example, many people have seen, and so we're going to spend more time with it, okay, than right now, and this is called matrices. Okay. Or arrays. Matrices or arrays, etc., etc. Okay, so let me tell you what those are. So we know what a matrix is. It's it's things with a bunch of numbers: 7.2 minus 8, 6.4, 12, 0, 1, 6, 9, minus 7.1. 14.8, 12.3, and 38.4 with a minus in front of it. Okay, anyways, this is a 3 by 4 matrix, and it's just an array of numbers. Okay, a multi-dimensional array of numbers. Okay, if you want, you can think of the regular numbers as just one number, as just a 1 by 1 matrix. Okay, now we want to talk about not a matrix, we want to talk about all matrices, and we want to use a different thing, okay, and so we form, okay, notice here, the entries are real numbers, so I want to talk about real mat. This is a category of real matrices. Let me tell you what the objects are. The objects are the natural numbers. Okay, so the objects are 0, 1, 2, 3, 4, etc., etc. Those are the objects. Okay, and a morphism from, just want to make sure I do it like, okay, from M to N, okay, is, so a morphism from M to N is an M by, or, okay, so I wrote by, and this could be by M matrix. So it's a matrix with N, like Nancy, rows down, and M across like that. Okay, so those are the morphisms. Now, again, there are a lot of N by M matrices, and so there's going to be a lot of functions from there to there. But this thing satisfies all of this, okay? But notice, the objects have no structure whatsoever. They're just natural numbers. They're ways of keeping track of the matrices, keeping track of the sizes of the matrix. Okay, well, let's see if we can get into a little bit more details about these. Let's erase this. Okay, and it goes as follows. If you have M and N and P, okay, and you have a morphism from M to N, and you have a morphism from N to P. So let's write this as follows. This is a matrix, and it has N rows and M columns. Now let's say you have another morphism from N to P, so you might call that B, okay, and it's going to have P rows and N columns. Okay, main point is this number is going to match up with this number. In other words, they're both N, and so you can actually multiply them. If you don't know what matrix multiplication, stop the video and go look it up, but it's you're going to have to know matrix multiplication, and so this is B P N times A NM. And that's matrix multiplication. Okay, so let's do it. The sources and the domains and codomains of all the morphisms are basically natural numbers, telling what the number of rows and what the number of columns are. Okay, and the maps are basically the matrices themselves. This is very interesting because we're defining the category mat, but it's not the objects which form the matrices, it's the morphisms. Okay, so let's go through it. Namely, okay, for n, there's a special map from n to n called identity on n, and basically that is the matrix with a bunch of ones down the diagonal and 0 everywhere else. So that's an n by n matrix with ones down the diagonal and everything else 0. And when you multiply with this matrix with any other matrix of size n, the appropriate size, on one side or the other, you get back the original thing, which means this is the unit. So you have the unit law. And turns out matrix multiplication is associative. Conclusion, the category of R matrices is a category. This is a category. Okay, great. But you know what? So far, all the matrices I've talked about had real number entries, but we're going to have lots of other type of categories of matrices. So let's start from the top. Well, don't start from the top yet. Well, let's just talk about regular. You could have natural number matrices. You could have, so these are matrices where the entries in the matrices are natural numbers. You can have whole number matrices, positive or negative whole number matrices. You could have rational number matrices. We just talked about real number matrices. Okay, you could have complex number matrices. We're going to spend a lot of time when we talk about quantum things. We're going to talk about that, etc., etc. But there's something else also, and these are called Boolean matrices. And these are matrices just with zeros and ones. Okay, and we're going to deal with those also a little bit later on. Main point, if you want, and we're going to formulate this a little bit later, these guys, well, let's leave that out for a second. These guys are well, I'm going to use the word, but I'm not going to explain it. It's a subcategory of these guys, which is a subcategory of these guys, which is a subcategory of these guys, which is a subcategory of these guys. And the idea is all numbers, all complex numbers have real numbers in them, they have rational numbers in them, they have positive, negative, etc., etc. Boolean matrices are a little bit more complicated. But anyways, don't want to talk about them right now. Great. Okay, new topic. This is a topic that's on the cusp between mathematics, set theory, combinatorics, etc., etc. Okay, and these are called relations. Okay, not doing good with the stupid pens. Don't want to use the other one. Let's see what that is. Okay, so the idea is as follows. Given a set S and a set T, you can look at the Cartesian product of that. Those are all ordered pairs with elements from here to here. Okay, before I do that, you might say, oh, he's going to talk about functions from S to T. This is a little bit more complicated than functions, a little bit more general than functions. So I'm going to talk about ordered pairs. And then a relation is a subset of ordered pairs. Okay, so there are certain things S that are related to certain elements T in there. Okay, so these are called relations. Okay, and we have a certain way of talking about them. Okay, so I want to talk about the category called rel for relations. Okay, and I have to tell you what the sets are. Oh, I'm sorry, what the objects are. The objects are, ready? All sets. Okay, I'm being a little bit, all sets. Those are the category of relations contains all sets. Okay. I just want to go over here and remind you what set is. Okay. Here, the objects were all sets, and the morphisms were functions. Okay, so we dealt with that. That was our first example in this video. Okay, now here the objects are all sets, just like that, but the morphisms are relations. Okay, let me show you how that works. So R, we're going to write R as, we want to think of it as kind of a function, so we're going to do it as follows. S to T, but with a slash across the arrow. Okay, and the way to think of this is R is a relation, I'll say from S to T, but that doesn't really make it. It's a relation between S and T. Okay, great. Now we could have another relation also. So let's write this again. S to T, we'll call this R. Okay, and then we can have another relationship from, cross this out, T to U, which you're going to call Q. Okay. And now the main thing is we're going to compose these relations. So again, a relation is showing a relationship between elements in S and elements in T. Q, I'm going to erase this, we don't need this right now. Q is showing is a subset of those elements between T and U. T and U. Okay, and now I want to talk about composing this. Okay, and this is going to be a relationship between S and U. Okay, and we're going to call this Q circle R. First do R, then do Q, and I have to explain to you what this is. So this is going to equal to, again, what is this? These are elements in pairs of elements of S and U. So little s, little u, such that there exists a T, member of T, such that S comma T is a member of R, and T comma U is a member of Q. Close. Okay, so let's go through this again. R is elements of S cross T. Q are elements of T cross U, and now we have Q composed R are elements of S cross U. Which ones? Well, those which can be matched up with an intermediate T. So let's do this. Okay, so which U are related? Well, if there's some guy in here such that there's a mapping from here to here, there's a relationship between that guy and that guy, and there's a relationship between this guy and this guy, then there's a relationship between this guy and this guy. So it has a feel of composition. Think about functions. What does it mean, the composition of this to this? Well, it says if you start here, you do this function, you get some element in T, and you do that element, you do that function, you're going to get some element in U. So similar type of thing. You need that intermediate thing. Okay, so this is called composition of relations. Okay, this is called composition of relations. And guess what? Relations composed associatively, and there is a unit. We're going to leave out what that is in a second. And so we get a category, and the category is called rel. Okay? And the way I want you to think of it is, I want you to think of set and rel are very similar to each other in the following sense. This has objects are all sets. This has objects are all sets. This has all relations. This has special types of relations called functions. I'm going to spend a little time talking about that. Special types of relations called functions. Okay? And so this kind of, you should think of this as what's called a subcategory. It's kind of like a subset. The objects are always the same, but here there are more morphisms because you can talk about relations. Functions are special types of relations. Okay, and we want to get into that, and so we want to talk about this. Okay, so what does it mean that functions are special types of relations? Okay, and so we have a lot of different properties of relations that we want to talk about. Okay, so I'm going to now talk about 4 properties of relations. Okay, so one is called total valued. So let's back up for a second and remember what we're talking about. We have R is a subset of S cross T. Okay, and I want to tell you when is R a total valued relation, etc., etc. Now, while I'm doing that, I want to show you a Venn diagram. The Venn diagram is on page 593 in the book. It's a nice Venn diagram that shows what the relationships between these things are, and we're going to talk about that. We're going to build it as we go along. So we have relations, all relations. Okay, and we might say this as follows. This is from S to T, like that. Okay, here I wrote it as a subset. Here I wrote it in that notation. Okay, so now we're going to talk about special types of relations called total valued. Okay, and let me see what that means. Okay, it says let's do that underneath. We need more room. Okay, sorry. Total valued. Okay, and what's this about? It says for every S member of S, there is a T. T member of T such that S comma T is a member of R. Okay, so total valued means for every one of these guys, there's some guy here. Now there could be more than one guy here, but that's fine. So this is called the total valued relation. Okay, and we're going to write it like this: total valued. Okay, so again, think of relations as relating these guys to these guys. Some of these guys might be loners and they're not related to any of these guys. But in a total valued function, every one of these guys has somebody in here that he's related to. Okay, next, single valued. Okay, and what does that say? For every S member of S, comma, there is, I'm going to change this as follows. There is at least one T, okay, such that this is true. There is at most one T, member of T, such that S comma T is a member of R. Okay, so it's exactly the same. This just says there's at least one. So for every little s, there could be 1, 2, 3, 4, 5 things. That's what total valued is. Single valued means for every single guy in here, there's at most one. What does that most one mean? It could be 1 or 0. But the main point is you can't have one guy here that's related to 2 guys in T. When it's single valued, you don't have S going to two different guys. Okay, great. So we're going to call this single valued. Okay, good. Okay, now what do you call these guys in here? Okay, what you call these guys are functions. Okay, what's a function? A function gives every one of these guys one of these guys. Every single one, it gives one of these. So something that's at least one and at most one is exactly one, and that's the definition of a function. Okay, so for every S, there is exactly one T that's in the relation. So if you're both total valued and single valued, you're a function. Okay, great. Okay, two more properties. One is 1 to 1. We saw this before about talking about sets, so let's just say what that is. It says for every T member of T, there is at most one S member of S such that S comma T is a member of R. Okay, so that's 1 to 1. Let's just say what that means. It says for every guy over here, there's at most one of these. There can't be two guys in S that go to T. Okay, that's 1 to 1. Okay, and we write this as follows. This is a 1 to 1 function. Okay, and next is onto. Okay, and this says, and we actually did this already, so let's just do it quickly. For every T member of T, there is at most, at least one S member of S, such that S comma T is a member of R. Okay, so for every T, so every guy in here has something, could be 1, 2, 3, 4, something from S to T that's relating it. So there's a certain symmetry here. This is making requirements on S, on elements of S. This is making certain requirements on the output T's. Okay, let's finish up this diagram. This goes like this. Okay, so in this loop you have functions. These are 1 to 1 functions. These are onto functions, and these are called isomorphisms. Okay, we saw that before when we were dealing with this. Okay, great. I want to do something a little bit quickly, but it's very cute. It's very nice. And the idea is as follows. For every relation, there's another relation called R minus 1. And R minus 1 goes, if R goes from S to T, R minus 1 goes from T to S. So let me tell you what the relation is. Little s, little t comma s is a member of R minus 1 if and only if little s comma little t is a member of R. And the idea is as follows. Take the elements, flip them. So this is called the inverse relation. It has the same information here, just turn them around. Okay, now you can compose relations. We saw that 2 minutes ago, but you can also compose relations R with its inverse. And I just want to show you a quick way of describing these 1, 2, 3, 4 properties using composition. Because one of the things we said, the central aspect of all category theory is that the morphisms is the right way to describe things. You should describe the properties of things through their morphisms. So we're going to do that right now. Okay, and it goes as follows. total valued means the identity of S is a subset of R inverse composed R. Okay. R composed R inverse is a subset of identity on T. Okay. Again, I'm just going to say this. It's going to take time to see it, but basically what it says is that if you start with T and do the inverse and then compose it to and get back and compose. If you start with T and look what's related to S, and then you get back and you see how it gets back, S to T, the board got a little bit too cluttered and I need all the board space I need, so we erase that. Okay, so what does it mean single valued? It means if you start with something in S, go to T, and then go inverse of it, it's a subset of IDS. In other words, there's only one thing that can start in S and go back and come back to that, only S going to S at the end of that, and the same thing here. Okay, these take a little time to see, and but the main point is there's a certain symmetry here, there's a lot of symmetry here, and it's very important to do it. Great. Okay. Now I want to talk about a new category, and the new category is called PAR. Okay, and it's similar to set, and it's similar to rel, which we just saw. Okay, and it goes as follows. They all three have objects are sets. Oh, sorry, all sets. Objects are all sets. Okay, here the morphisms are functions. Here the morphisms are relations. And now we have to talk about the morphisms here. What they are is they're partial functions. Now, what do I mean by a partial function? So let's talk about it. You have R going from S to T. It's a relation. But if this relation is single valued, then it's a partial function. Let's just remember what single valued means. It means for every guy here, there's at most one guy here that's related to it. For every little s, there's at most one t that's related to it. Now, what do I mean at most? Well, there could be a t and there could be a zero. So there's at most one. So there could be one t or there could be zero t's. What we say is as follows. If there's one t, then it's a partial function, and on this little s, you get a t. If it's not related, so then if there's no t, if there's zero t's, then there's nothing related. So the way to think of a single valued is it's a function, but it doesn't necessarily have a value on every single input of S. So that's called a partial function. Some inputs, some little s's, don't have a value. So a partial function is a single valued relation. Okay. A partial function is a single valued relation. That's very good. Now, what's total valued? Okay, or let's put it another way. A function equals single valued and total valued. Okay, what does that mean? Well, that means single valued means there's at most one t. For every s, there's at most one t. Total valued means for every s, there is at most, there's at least total valued means for every s, there's at least one. Okay, now if you have something that is both single valued and total valued, then there's at most one and at least one, there's exactly one. Okay, and that's exactly what a definition of a function is. What's a function? For every single guy, not just partial, but for every single guy in S, there is a t that corresponds to it. Okay, so we have functions. So let's go through it. Functions are special types of relations. So you have relations, and you're going to have partial relations. Partial relations are special types of relations, okay? And then you're going to have special types of partial relations, which are also total valued, and those are going to be actual functions. Okay? And then you can go on and talk about one-to-one functions and onto functions, and things that are both one-to-one and onto, those are called isomorphisms. Okay, so I'm sorry, I'd like to rewrite these three categories because they're very, very important. And they, again, set, we're going to talk about every single day, every single video, but par and rel are also extremely important, and lots of examples show up talking about them. But the way to think of them is as follows. Set, par, and rel, okay, all three of these have objects as, the objects are all sets, okay. These guys have the most morphisms, these guys have the least morphisms, these guys have the intermediate. The most morphisms is all relations. A little restrictive of that is a special type of relation called par, and a little restriction of that is a special type of partial relation, namely, a special type of partial function, namely total functions, just functions. Okay, there's a little bit of a problem here. If you think about it, why is this called set? In other words, they all have objects as sets. Okay, but this guy we talk about, the morphisms are relations. Here we talk about the morphisms are partial functions. Here we should also say the morphisms, since they're all, the objects are all sets, the morphisms, so this category should really be called fun, as in function. Okay, that's somewhat of a joke. Anyways, the reason why we don't call it fun is simply because set is used so often, and everybody knows what it is. So we don't want to do it. But again, sometimes we're going to see these categories are named after their objects. Sometimes they're named after their morphisms, and that's okay. I'm going to use a word which I'm not going to define, but you know what it means already. This is a subcategory of this. This is a subcategory of that. Okay, great. Okay. Okay, good. Now, I want to talk about special types of relations, but relations not between two different sets, but a relation on a set by itself. Now, we saw this already when we were talking about equivalence relations in chapter 1, but let's do it again. So we have R is a subset of S cross S, not because S cross T, but S cross S. Okay, and what this is about is as follows. You have this set S, and you're going to have different elements related to other elements, and R tells you what's related to what. Okay, so we saw this already, again, in chapter 1. But I want to talk about different properties of this. Well, let's go through some of those properties. We've seen them before. Reflexive. What does that mean? It means for all S comma S is a member of R. Everything is related to itself. Symmetric. It means if S comma, well, S1 comma S2, if S1 is related to S2, that means, that implies that S2 is related to S1. Okay. Okay, transitive. I'm sorry. I'm gonna go back to talking about X and Y. So if X comma Y is a member of R, and Y comma Z is a member of R, that implies that x comma z is a member of R. Okay, so that's transitive. Another one is called antisymmetric. Antisymmetric. Okay, and basically that says if x comma y is a member of R and y comma x is a member of R, that implies that x equals y. Okay, it's a bad name. Antisymmetric is a bad name because it's, but what it says is if one thing is related to the other and the other is related to it, then the only way that can be is if they're equal. We'll see an example of this in a second. Okay, and finally, this also we did not see before. A relation on a set to itself is total, not total valued, but total if for all xy we have either x is related to y or y is related to x. One or the other is true. Okay, and if you want, you can think of a set of real numbers, and the real numbers is like this. Okay, and given any two numbers, x and y, one is less than the other or the other is less than it, or they're actually equal. Okay, now, just like I wrote in red last time how to think of these properties of relations, I'm going to write it here also, not necessarily in a more categorical way, namely, there's the identity relation on S, and that is a subset of R. In other words, in order to say that R is reflexive, it means that for every pair, for every element S, S comma S is in R. Okay? What does it mean to be symmetric? Well, we had this property of, we had this other relation called the R inverse, and if R is equal to R inverse, in other words, if two things are related, then their opposite is also related. Transitive means as follows: R composed R, and here we have composition, and I told you composition is something we want to think of these things as functions, as morphisms in a category, so we like talking about that. R comma R is equal to R. I'm sorry. Is a subset of R. Okay, well, what that says is if you have two things and you compose them like this, x and y, y and z, x and y, y and z, then you can add x and z. Antisymmetric says R intersect R inverse. If something is both in R and it's the opposite's also in there, okay, the only thing that's has that property is the identity on S. Okay, and finally, total says basically something symmetric to that. R union R inverse is equal to S cross S. In other words, if you everything's either here or there. Okay. Okay, great. Okay, so that's nice. Okay, there's a nice Venn diagram that goes along with this. I'd like to do that. I'm sorry, I got to use the thick marker, and the thick marker doesn't erase so nicely, but that's okay. Okay, so nice Venn diagram goes as follows. Okay, you have all relations from S to S. Okay, so these are all relations. Okay, but now I have special types of relations. Okay, one is called transitive. Okay, This is in the book on page 593. This is called reflexive. Oops. I'm going to have to get bigger than that. Hold on, sorry. The overlap has to be bigger because we have a lot more things to talk about. Okay, so this is transitive. Okay, and this is reflexive. Okay, okay, great. Now, what do you call the overlap? What is a relation that's both transitive and reflexive? We call it partial order. I'm sorry, we call it a pre-order. Okay, sorry about the squeaking. We call that a pre-order. Okay, now let's just go over here and say what that means. But we're going to write pre-orders with this. We're going to write a relation that's a pre-order as the symbol this. Now instead of R, we're going to call it like that. Okay, and so transitive means if X is less than or equal to Y and Y is less than or equal to Z, this implies X is less than or equal to Z. Okay, so that's what transitive means. And reflexive basically means that X is less than or equal to X. Okay, so anything that satisfies these two things is called a pre-order. Okay, hold on, we're not finished. Okay. Next, we have relations are also called, certain types of relations we call symmetric. Okay. And we had in section 1.4, we talked about equivalence relations. What's equivalence relations? They are reflexive, symmetric, and transitive. So anything within here is an equivalence relation. Okay, good. Next, there's something else called antisymmetric. Okay, there's a slight overlap here. We'll talk about that in a second. Okay, and what do you call a relation that's transitive, reflexive, and antisymmetric? We call that a partial order. Okay, so that's a partial order. In here is a partial order. It's transitive, reflexive, and antisymmetric. Let's do what a partial order is here. So we have to tell you what antisymmetric means. It basically means if X is less than or equal to Y and Y is less than or equal to X, okay, this implies that X equals Y. Okay, so this is a partial order. Okay. Besides that, we have special types of partial orders, which are total. Okay, we don't want to. I'm going to make this a little bit too complicated. There is something I told you. Symmetric and antisymmetric is not really. You would think that if something's symmetric, it's not antisymmetric. But there is one thing. The identity relation is an equivalence relation. It's a partial order. It's symmetric and it's antisymmetric. Okay, we're not going to get into that at the moment. Okay, great. So now that we understand what these partial orders are and pre-orders, okay, we have to talk about maps between them. Okay, and the idea is as follows. Let's talk about pre-orders, but whatever we say about pre-orders works in partial order. So let's say you have a map F from P, from this pre-order to this pre-order. I'm going to make this a different type of less than or equal to. So you have this pre-order and this pre-order. What's a map between them? Well, it's a map. It's just like we saw this before. It's a map that's going to preserve the operations, the other operations, or the other relations. So it's going to be a map from P to Q. P is a set of elements, Q is a set of elements, but we also want as follows, that if X is less than or equal to Y, this implies that F of X, okay, this is called preserving the order, is less than, funny less than, y. Okay? Such maps, such functions that satisfy this requirement are called order preserving functions. Okay? Okay. And again, P could be a pre-order, P could be a partial order. Both of these have the same idea. And now we have to talk about two new categories that we didn't see before. Okay? And one with two funny names. One is called PREO, pre-orders, and one is called PO, partial order. Okay? The objects are here either pre-orders, and here they're all partial orders, and the morphisms are order-preserving functions. The morphisms in here are order-preserving functions. The morphisms in here are order-preserving functions. This is a subcategory of these. These are special types of Nope, sorry. This is a special type of this, so I guess we would write it like this. Okay, this is a subcategory. This is a subcategory of this. Partial order, right? No, so then no, sorry. That's a subcategory of this. Pre-orders are a special type of partial orders. Okay, great. So these are the two categories, and again, they show up. Main point about these two categories is between any two objects of either of these categories, there's exactly one. Oh, no, that's not true. Okay, sorry, that's not true. Forget about that. Okay, so lots of morphisms between objects here. Very nice. Okay, I'd like to show you an example that's going to show up over and over of a partial order, and the idea is as follows. Ready? The idea is as follows. We don't want to use this. Okay. Take any set S. Look at the power set of S, namely all subsets of S. Okay, and this is a partial order. Okay. The subsets of S are all ordered under inclusion. Okay, so let me give you an example. Take the set A, B, C. You can get something simpler than that. Okay, and then take the power set of that. Okay, that's going to have 8 elements. And I want to describe those 8 elements, but I want to describe them as a partial order. Okay, and so one of those elements is going to be the empty set. That is a subset of this. The other one is going to be the whole thing. That is a subset of this. And there's a few more. So the set that only contains A, the set that only contains B, the set that only contains C, these are subsets of this. And this is an inclusion. The empty set is included in here. This is included in here. This is included in there. Okay. Next, we have the set that contains AB, the set that contains BC, and finally the set that contains AC. Okay. This includes into this. This includes into this. This includes into this. This includes into this. This includes into this, and this includes into this. Okay, and all these 2-element subsets include into the larger one. Okay, so you have some type of cube. If I would have drawn it a little bit more carefully, you would have a cube standing on one edge. Here's one edge, and here's another edge. So that's very nice. But again, for any set S, the set of subsets is a partial order. Okay, we have two more examples to do of categories. And again, I have to apologize for the length of this class. The main point is as follows. We're going to see these categories, all of these categories, over and over and over throughout the rest of the class, throughout the rest of the book, etc., etc. We're going to see more examples also, but a lot of the examples are going to be what we see here. And so we have to get used to them. They have to become old friends, okay? And we have to be able to mention their names and automatically know what their objects are, know what their morphisms are, and see that they're a category, okay? And we're going to relate all these different categories to each other, to other things, etc., etc. We're going to show more structures in these categories. These are going to be our building blocks for the rest of the course. Okay, I want to talk about something for a second, and I want to talk about, let's say, this, the rational numbers, the real numbers, the complex numbers. Okay? And what I want to do is, I want to read to you something from the book. Okay? The book has these things called important categorical ideas sprinkled throughout the book, and one of them shows up here. It's on page 53. It's called Important Categorical Idea, okay? And it says contexts are central. Okay, so the question is as follows. Look at the rational numbers, look at the real numbers, look at the complex numbers. What are they? In what category are they? Well, and the answer is that there's a lot of answers to that question, okay? And so for one thing, these guys are sets of numbers, so they're objects in the category of sets. On the other hand, they're all fields, so they're objects in the category of fields. However, they're also rings. Let's remember what a field is. A field is two operations, plus and times, but they also have inverses. So plus has minus, and times has division. Okay, great. But they're also rings, which are weaker forms of fields. They're also monoids. They're also groups. They're abelian groups. All the multiplications are abelian. They're also magmas. They're semigroups. So these three guys sit within those categories also. Okay? What else? They're also, you can give topologies on these sets. Say what numbers are near other numbers. So they're objects in the category of topological spaces. They're also types of vector spaces. I guess they're all, they're all rational. They're all rational vector spaces. Okay. They're also partial orders. They're also all pre-orders. Okay. I'm looking at this because there's so many and more. Each one of them is a partial order. So not only are these elements of the category partial order, they're objects in the category of partial order, but each one of them is a partial order. So there's lots and lots of ways of looking at these things, and that's very, very, very interesting. So this is what we say. When I talk about the complex numbers, I have to say, yes, it's an element of a category, but the question is, which category? And so we have to say which category it is so that we can know what context we're talking about. I just want to read a cute line at the end. Okay. Let us stress the point with an example. While a group theorist looks at the real numbers, so we're talking about the real numbers, while a group theorist looks at the real numbers one way, a topologist looks at the real numbers in another way, a physicist and a computer scientist look at the real numbers in their own different ways, the category theorist must look at the real numbers in all possible ways. So we have to see it in its context, but we have to realize that they show up all over. Okay, great. Like I said, we have two more examples of categories that we want to talk about. Okay, one is called, we'll write it with blue, okay? One is called circuits. Oops, CIR, sorry. So these are logical circuits or things like that. Okay, and so this is part of computer science, this is part of logic, etc., etc. So you might have seen this before. There are logic gates. This is called the AND logic gate. Okay, sorry, we're not going to do that. Okay, there's other, so basically electricity comes in here, and if there's electricity coming in both of them, then this comes out also. Okay, and besides that, there is the OR gate. Okay, besides that, there's the NOT gate. Okay, another gate that we're going to see a lot of is, whoops, not a lot, but the NAND gate. So this is NOT. Okay, this is NAND. Sometimes there's a little circle over there. Okay, there's NOR, there's XOR, there's lots of gates, and these gates describe what happens when electricity comes or when a bit is on or off, and how these things work. Not interested in right now of how this works, and if you don't know it, that's fine too, because there's going to be enough definitions without it, but it's something to see. Okay, these are the building blocks of all logical circuits. Okay, and so your computers are built up of complicated circuits like this. Well, I want to think of this as a category, so I have to tell you what the objects are. The objects are the natural numbers. Now, we saw something similar to this when we were talking about matrices, where the objects are the natural numbers. Basically, there in matrices, and here also, the objects are like bookkeepers. They're keeping track of where you're coming from and where you're going. They're not really important. The important things are the morphisms. So F from M, a natural number, to N, a natural number, is going to be a circuit with M input wires and N output wires. Okay, so you're going to have M inputs and N outputs. The way we write this is as follows. Here's a typical circuit. Okay, and so we'll have M input wires and we'll have N output wires. Okay, and guess what? We can compose. So if you have N output wires here, you can, we'll call this C, we'll call this C prime. You can have P output wire, N input wires here and P output wires. Well, if you look at this all together, this circuit has M input wires and P output wires. And so that's very, very nice. Okay. Also, there's a stupid circuit, we'll call it identity on N, which basically has N input wires and does absolutely nothing but returns the same N inputs to the outputs. Okay, so that's the identity circuit. And guess what? Two things. You should be used to this already. One, circuit composition is associative, and the identity acts like an identity, namely, if you compose one circuit followed by the identity, you get the original circuit. And you can do it on both sides. Okay? Conclusion, the category of circuits is the collection of circuits forms a nice category. Okay, I just want to look at these things. This is an element of 2, 1. 2 inputs, 1 output. This is 2, 1. This is also an element in there. This is an element of HAM 1, 1. Okay? In the book, I have a nice big example with an element of HAM 6, 3, I think. Maybe 6, 2. It's a complicated circuit with 6 input wires and 3 output wires, or 2 output wires. I don't remember. Okay, so lots of different examples there. Okay, that's our second to the last example. Okay, now finally our final example of categories. This is built on something that we saw before. We had the category prop. Let's just remember what those are. This is a category about logic. The objects are propositions. Propositions are statements that are true or false. Okay, and we can either have no morphism between them, which means there's no relation, or we could have at most one morphism in between them. And basically, there is one morphism if P implies Q. Okay, so we saw that before. That was one of our first examples. And now I want to show you another category. This is called proof. Okay, the objects are the same things, propositions. And now what they are is, now what the morphisms are if there exists a morphism, it's a proof that if you assume P, you're going to get out Q. Main difference between this and this is there could be many proofs that if you assume P, you get out Q. So we're talking about some logical system. We're being very formal. We're being informal about a formal system, et cetera, et cetera. Okay. Okay, great. Now, if you have a proof that if you assume P, then you get Q, and you have another proof that if you assume Q, you get R, then you can compose the proofs, basically put one proof on top of another proof, and you get a proof that if you assume P, you get R. Composition. Okay, guess what? Composition is associative. 2. For every proposition, if you assume P, you get P. Okay, there's a trivial proof. There might be more than one trivial proof, but that's okay. We don't want to talk about that. Anyways, conclusion. Just like this is a category, this is also a category. Notice the following thing. And we're going to see this later on in chapter 4, we're going to talk about this. If there is a morphism from here to here, then there is a morphism from here to here. In other words, if your proof system works, if you can prove from P that P implies Q, then P does imply Q. That's it. Okay, so these two categories are very, very, very related to each other. Okay, I wanted to just mention one thing about circuit. There's a slight problem with the definition of circuit, and it has to do with the identity morphisms. It has to do with the wires. Okay, anyways, I talk about it in the book, and I go through what the problem is, and I go through possible solutions, and so it's a solvable problem. Okay, so that's the end of our examples. We'll talk about one more topic, two more topics. Not in our examples, but two more topics. And one is there's types of categories. And the idea is as follows. When we talked about categories, when we started talking about categories, I said the objects are a collection, the morphisms are a collection. I didn't say what a collection was. And I didn't want to say what a collection was because I didn't want to get into the set theory about that, of what's the difference between a set and a class. But basically, sets, proper sets are somewhat smaller, classes are somewhat bigger. Okay, but the thing is that the examples show there's all types of examples, and you can't just say, "Oh, I want to only talk about sets," because that's going to make your category theory very, very uninteresting. Anyways, so we have to keep track of the sizes of our objects and of our morphisms. Okay, and so we have three different types of categories. There are others also. One category is small, and what this says is the objects and the morphisms are sets. Okay, so that's called the small category. The partial orders that we saw are small categories. The one object categories, monoids, are all small categories. There the objects are only one element. Okay, so that's really small. Okay. Okay. As opposed to that, we have large categories. Okay. Objects or morphisms are classes. Okay, so that's what the opposite, well, I don't want to say the opposite, whatever, but if one of them, the objects or the morphisms, are classes, then the category is called large. And we have something that shows up very, very much, and this is locally small. Okay, here the objects are usually large, and the morphisms are usually large, but a category C is locally small if for all A and B in C, take any two objects, ham A comma B is small. So again, the objects are large, they form a class. All the morphisms together might form a class. But any two objects in particular, that ham forms a set. Okay? So most of the examples that we have are like that. So for example, the category of set. The collection of all sets is a class. The collection of all functions is a class. But between any two sets, you have a set of morphisms, ham set. Okay? Groups, topological spaces, manifolds, they're all locally small. Okay, they're not small, they're not large, they're locally small. I'm sorry, they are large. They're in general large, but they're locally small. Okay, so those are things. Just want to talk about an interesting. Well, let's look at the collection of all one-object categories. I'm sorry, one-object sets. So here's our favorite one-object set. Here's another one-object set. Here's another one-object set. Okay. There is not an infinite amount. There's a class of one-object sets. Okay, but between any of them, there's at most one morphism. I'm sorry, there's exactly one morphism between any of them. So that's even smaller than locally small. There's exactly one morphism between any one of them. Okay, let me just tell you how the chapter ends. I'm not going to go through the details of this, but it's worth it for you to go through the details at some point. Okay, so we started the chapter off giving a definition of categories, and so what I would like to do now is give you another definition of categories. So the first definition of categories said there are objects and there are morphisms. Okay. Okay, the second end, these objects and morphisms, there's functions in between them, there's operations on them, etc., etc. We spent a lot of time talking about this, and we spent a lot of time over the past 2.5 hours stressing the importance of morphisms. Great. So the second definition doesn't have objects. It doesn't talk about objects. It just says there are morphisms. Okay, and so this is called, so beforehand, when you have two of them, this is called a two-sorted definition. So there's two sorts of things, objects and morphisms. Now, the second definition is a one-sorted definition. We're only dealing with one thing. So basically, a category A is a collection of morphisms of A. Okay, and it has different operations and satisfies different requirements, but the idea is as follows. You ready? What you have is a morphism here, F. So this is a typical element in here. Now you might say, where does F go to? Where does F come from? Where does F go to? And the answer is very simple. Domain of F. And this is codomain of F. Okay? So you should think of the arrow as the domain of F. And this arrow, so you have arrows coming and going from arrows, codomain of F. Okay? And you can describe all categories just like this. So what's a category? It's a set of morphisms. The domain and the codomain are meant to be thought of as, the domain and codomain are meant to be thought of as identity morphisms. Okay, so that's all I want to say about section 2.1. I'm sorry, it's a long section. We introduced all the major players that we're going to see here for the rest of the book, for the rest of these lectures, for the rest of the course. So we had to spend time getting used to them and learning all about them, and et cetera, et cetera. Okay, it's great whenever you see a new concept to go through some of the examples and see, do these things have these properties, or what is this over here? Here's an idea. How does it relate to this example? How does it relate to that example? Okay, so we're on our way. Okay, thank you very much. I'm sorry, let me foreshadow a little. Okay, so this is the beginning of chapter 2. What we do for the next few sections is as follows. This is 2.1. Section 2.2, we talk about different properties of categories, different things, different types of morphisms within a category, different types of objects within a category. Section 2.3 talks about related categories. So whenever we have a category, we're going to have other categories that are somehow related to it. We're going to talk about subcategories, which I mentioned a few times. We're going to talk about other things like opposite categories, quotient categories, Cartesian product of categories. So you're going to have related categories to an original category. Okay, and then the end of chapter 2, we go through these vector spaces. So we talk about, we give a whole class on basic linear algebra from the categorical point of view. So that's the beginning of chapter 2. That's chapter 2. Anyways, looking forward. Take care.